Okay, so welcome back everyone to the Isogeny Club. So today it's my pleasure to present Eli Orvis from CU Boulder, who will be talking about the Ihara zeta function of abstract isogeny graphs and modular curves. So the stage is yours, Eli.
Great, thank you. And thanks to the organizers for inviting me. I'm going to talk about a recent preprint that was just put up on arXiv a couple of weeks ago about Ihara zeta functions of abstract isogeny graphs and the relation to modular curves. And this is all joint work with Junbo Lau, Travis Morrison, Gabrielle Scullard, and Lucas Sobernig. So I want to start with a little bit of a very brief cryptographic motivation because I know a lot of the audience is cryptographers. So it's something that came up in a fairly recent paper, the supersingular elliptic curves you can trust paper, is expansion properties of isogeny graphs with level structure. And so in particular, that paper used non-backtracking walks, so expansion properties of non-backtracking walks rather than just any walk, in the isogeny graph GPL with Borel level structure. And they use this to provide a zero knowledge proof of knowledge of an isogeny, right? So this is kind of the cryptographic motivation for studying these expansion properties. And what we did in our paper is gave kind of a framework for studying expansion of non-backtracking walks in isogeny graphs with level structure, and in particular through their zeta functions. So zeta functions may be a scary word for those of you that are more in cryptography than in math, but I'll take things really slow and I'll point out how zeta functions of graphs are these objects that capture particular expansion properties. So they're really related to the story of, when these graphs are Ramanujan, about uniform distribution of non-backtracking walks of certain lengths, that kind of thing. So I want to start with just a quick primer on like zeta functions in general. So you maybe have at least heard of the Riemann zeta function. Probably most people have at least heard of it. If you haven't seen it written before in this way, it can be described by what's called an Euler product. And so you can write the zeta function as this product over all of the prime numbers of 1 minus p to the minus s is the variable, all to the minus 1. And this, you can kind of, maybe guess from writing it this way, that this is related to the distribution of primes, right? So, the famous Riemann hypothesis tells us that the zeros of the Riemann zeta function encode information about the distribution of primes and kind of give us really specific estimates. If we understand where the zeros are, we can give really specific asymptotics about where the primes occur in the regular integers. So that's like the classical story, and why we call these things zeta functions. It's just a zeta function is something that reminds us of the Riemann zeta function. But there are other zeta functions that appear in other places in math. And in each case, right, they're related to the distribution of some object that we care about that kind of plays the role of prime numbers. So for example, one you might be familiar with, if you're more on the algebraic geometry side and you're interested in things like point counts over finite fields, is the Hasse-Weil zeta function of a variety. So you can really ignore most of the adjectives in here. You can think of this as just taking x to be a projective variety, so a solution to some polynomial equations in projective space could just be even an elliptic curve. And it's defined over some finite field. And the Hasse-Weil zeta function is defined as this exponential of a sum that counts the number of points over different extensions of our finite field. And again, it has this product formulation that should remind you of the product formulation that we just saw for the regular Riemann zeta function. So here, instead of 1 minus p to the minus s, you have your variable u, and you have 1 minus u to the degree of the point, where the degree of the point just means the degree of the extension of FL where that point is defined over, right? So again, you can think, if you're just familiar with elliptic curves, you can just think of this as you start with a concrete equation like y squared equals x cubed plus x, and you look at how many solutions it has in, say, the field with 13 elements and then 13 squared elements, 13 cubed elements, etc. And you put those all together into this function, which you can then use to study the distribution of those point counts. And again, these zeta functions have a version of the Riemann hypothesis attached to them. And in this case, it's actually known to be true, unlike the actual Riemann hypothesis, by very deep work of Deligne and many other people that I couldn't even begin to describe, but we know that it's true. Okay, so in this talk, what we'll be interested in is zeta functions of graphs, in particular, supersingular isogeny graphs, right? These things that we care about as isogenists. And so in order to define a zeta function for a graph, what you would like to do is give an Euler product as some sort of product involving primes, right? Like just like we saw in the past couple of examples. But the question is, what should a prime be in a graph? And so the definition, which goes back to Ihara and some other people in like the 1960s, is that a prime in a graph is a closed walk containing no backtracking or tail, which is not a shorter walk repeated multiple times. So it's a cycle that's not allowed to backtrack. The tail means that you can't have backtracking essentially in the first and last steps. So you can't take one step out, do a cycle, and then come back along the same edge. And not being a shorter walk repeated multiple times just means you can't go over the same loop multiple times. But this leads to what turns out to be a fairly subtle question, especially in isogeny graphs, which is, what do we mean when we say no backtracking, right? So in general, right, so just for graphs as, general and combinatorial things, there's this definition of a graph using by Sayre, and this is usually what people mean, right? So in Sayre's definition, a graph is a set of vertices together with a set of edges, such that each edge has an identified source and target, and you have a fixed point free involution, J, which swaps sources and targets. So what you think of J as doing is identifying a pair of edges that are kind of opposite of each other, right? So the one edge goes from, V to V prime, and then J of that edge goes back, right? And then you say a walk has no backtracking if you never follow an edge by its opposite under the J function. So this is very nice as long as your graphs are sufficiently nice to be like basically undirected graphs. But of course, some things go wrong in the case of isogeny graphs, right? And so this definition, you really can't make supersingular isogeny graphs into a graph with this definition because of issues that come up with the J function. And in particular, things go really wrong for isogeny graphs with level structure. So, we'll come back to that as we build a little bit more theory. So before we get back to kind of what's going on with isogeny graphs, though, I just want to say a little bit about the types of zeta functions we'll be studying. So classically, we have these things called Ihara zeta functions. And what they do is they take the counts of non-backtracking cycles and they put those into a meromorphic function. If you are not familiar with any complex analysis and meromorphic is not something you're used to, just think a very nice function. In our case, it will even be just a rational function, like a ratio of two polynomials. So it's really something that you can work with concretely. So what's the definition? So you start with a graph. You can take it in the sense of Sayre or just an undirected graph. And then the Ihara zeta function is an Euler product, just like the previous zeta functions we saw. But we take the product over primes in the sense of the previous slide of 1 minus u to the size of the prime, which just means the number of steps in that prime as a cycle, right? And there's a small technical point that really our primes should be equivalence classes of primes. We don't want to count a cycle starting at one vertex versus starting a different vertex along the cycle as different. So we really take the equivalence class up to cyclic rotations. But the point of doing this is we have this Euler product, and we can use this to recover the number of non-backtracking cycles of a given length, right? So you take the log, you take the derivative, and you get just a usual generating function where the coefficients are the number of non-backtracking cycles of a given length. So this is why we can use these functions to, say, study the asymptotic number of cycles of a given length in the graph, is because we might be able to do some sort of analysis to look at the growth of the coefficients of this function as this generating series, and then understand the number of cycles, how that grows with m from that analysis. And another fact is that in the classical case, there's this very clean formula for the Ihara zeta function. So if you have a regular graph and you let A be the adjacency matrix, then the zeta function can be written as this rational polynomial, so or rational function. So this is why I said earlier, if you don't know things like meromorphic functions, you can forget about that and just think of this as a ratio of two polynomials. And to point out the kind of constants that show up here, in the numerator, the power of 1 minus u squared is 1 minus the Euler characteristic of the graph. So you've seen a little bit of graph theory. This is an invariant of the graph. It's related to the topology of the graph, but it's like a standard number that is associated to a graph that encodes a lot of information about the graph. And then in the denominator, you have the determinant of this function that involves the adjacency matrix, and then just the degree of each vertex. So the degree minus 1 appears to. One other fact that I just want to throw in that didn't fit on the slide, but to emphasize the relation between these zeta functions and expansion properties, there's a version of the Riemann hypothesis for Ihara zeta functions, and they satisfy this Riemann hypothesis if and only if the graph is Ramanujan. So the idea is kind of this denominator, this determinant involving the adjacency matrix, that's closely related. The zeros of that denominator are closely related to the eigenvalues of the adjacency matrix. And so they tell you things about the expansion properties of the graph.
We have a quick question in the chat. If
yes.
by Bruno.
Are there any yes, I see it. Should I just go ahead and answer?
Yeah, go for it.
Sure. Bruno was asking about constraints on u in the rational formula for like real u greater than 0. That's a good question. I think that actually these are meromorphic on the whole complex plane, except there's a few poles, right? So you have to avoid these particular poles, but other than that, I think that these converge everywhere. In fact, these you can see these as rational functions using this expression, and so that rational function is going to be meromorphic everywhere with just poles at the roots of the denominators. I don't know. I'll just to point out. I don't know if the Euler product definition necessarily converges everywhere, or if the rational function agrees on one piece and then gives you an analytic continuation to the rest of C. But certainly the rational function description gives you something on all of C. Cool. Okay. Great. So we have these functions. There's something you can actually write down and work with. That's the point of seeing them as a rational function. And they capture properties about, the spectrum of the graph. So expansion of walks, whether it's Ramanujan, these kinds of things. So what we want to do is study non-backtracking cycles in lots of different types of isogeny graphs, right? So we have the usual supersingular isogeny graph, but as we mentioned at the beginning, graphs with level H structure for various H's have been coming up more frequently in isogeny-based cryptography, and I'll give a short description of what this means in a couple of slides. But then also higher dimensional isogeny graphs. So this is like you have principally polarized abelian varieties, and you use L, comma, LLLL isogeny graphs. We'll mention those very briefly. They're not really a focus of the paper, but the framework also captures them. And in all of these graphs, we have a natural notion of backtracking that's given by the dual map. So you have an isogeny from one vertex to another, right, which is an edge. And then what you want to say is that the opposite of that edge is given by the dual. But in Serre's definition, we said that this opposite function, j, needed to be a fixed point free involution. And in even just the base isogeny graph, GPL, the dual can have both fixed points and not be an involution. So to see this for fixed points, there's a fairly simple example. So you can take the usual P is 3 mod 4, and you just write down the endomorphism ring of the curve with J invariant 1728. This is often written E0 in isogeny literature, but that kind of drives me crazy sometimes because I always think that it should be the J invariant 0. So I wrote it as E1728. But you can write down this endomorphism ring as an order in a quaternion algebra very explicitly, and the dual corresponds to quaternionic conjugation. So this equation you see at the bottom here, that the dual of the endomorphism 1 plus I is 1 minus I, is the same thing as minus I times 1 plus I, tells you that the dual is the same as the original endomorphism up to post-composition by an automorphism, right? So the minus I is an automorphism, and we see that the dual is the same as the original post-composed with minus I. And so because in the usual isogeny graph GPL, we identify isogenies with kernels, and therefore we identify isogenies up to post-composition by an automorphism. This is telling us that in the two isogeny graph, the endomorphism 1 plus I is represented by a loop, which is equal to its own dual, right? So if we just took the dual map to be our J function, it might not be fixed point free. And then it can also fail to be an involution. So to describe this, I just added a hand-drawn version of a picture from the Orientations and Cycles in supersingular isogeny graphs paper. But the point is, at the bottom, you have J equals 0. At the top, you have whatever J invariant. They give an actual prime and an actual example. But there are cases where you say have an isogeny phi going from J equals 0 to your other J invariant, and you can precompose by these two non-trivial automorphisms on J equals 0 to get two other isogenies. But when you look at the duals, you get one actual edge back, that's the phi hat, and then the other two edges corresponding to the other two isogenies out of J0 get identified up to post-composition by an automorphism. So the dual map won't act as an actual involution on this set of isogenies because, say, phi precomposed by zeta 3 squared goes to phi hat, which goes to phi and not back to itself. Right. So the dual map can also fail to be an involution when P is not 1 mod 12. Great. So abstract isogeny graphs showed up in the title, and these are something that we introduced to provide kind of a framework for addressing these issues. So it's a generalization of the idea of a graph by Serre, but now it can kind of hopefully capture the cases that we want. So we start with the same collection of data that Serre has, so a set of vertices and a set of edges. And then we have source and target functions we denote by S and T, on the edges. And then we have a function j, which acts on the edges. So this will be like our dual map. And then we also introduce a function L that acts on the vertices. And I'll motivate why we need that to capture the kinds of properties that we want in a couple of slides. But then the requirements on these J and L functions, instead of requiring that J is a fixed point free involution that swaps sources and targets, what we require is that the source of J of an edge is the target of an edge, and that the target of J of the edge is this L function applied to the source. So these probably seem a little unnatural. Maybe the first one is somewhat natural, right? The source of the dual should be the target of the original isogeny. The second one is motivated by some weird behavior in more exotic examples of graphs with level structure. So let's talk about that where this capital L function came from. So to see that, we need to dig into a kind of even worse failure of the dual map that occurs only in isogeny graphs with level structure. So we've seen that the dual might not be fixed point free, and it also might not be an actual involution on edges. But in isogeny graphs with level structure, things can actually go even worse. So to do that, I just want to recall the definition of a level structure and how isogenies work between curves with level structures. So if you haven't seen this before, a level H structure for H some subgroup of GL2 Z mod NZ is an isomorphism between Z mod NZ squared and the N torsion, considered up to precomposition by elements of H. So what this means is you've essentially chosen a basis of your N torsion, but you identify two choices of bases if they're the same up to the action of an element of H, thought of as a matrix in GL2 Z mod NZ. And so what should isogenies between curves with level structure satisfy? Well, they should satisfy some sort of commutative diagram that tells you that the isogeny respects the level structure. So say you have an isogeny psi on the bottom here, it's some isogeny from E to E prime. So it takes the N torsion on E to the N torsion on E prime. What it needs to satisfy to be an isogeny of curves with level structure is that if you take the level structure thought of as a map from Z mod NZ to En on the left side, and then you do psi, you should end up with the level structure on E prime that is your target, all up to action of elements of H. Right. So our isogeny graphs with level structure, we take our vertices to be elliptic curves together with H level structures, and our isogenies to be isogenies between them, but they have to respect the level structure in the sense of this diagram. So why does that mess up duals even further in some cases? Well, it's because the dual in GPLH might not even swap sources and targets. So the picture that I have in mind for this is looking at what happens to the level structure when you take an isogeny and then you apply its dual. So I've just taken two of the squares I had on the previous slide, and I've just put them next to each other. So we start with psi, which is an isogeny between E on the left here and E prime, and it takes the level structure phi to the level structure phi prime. Well, then if I do psi dual, I end up back at E, but what have I done to the N torsion across this bottom row? I've multiplied it by L, right? So I've acted by like the scalar matrix L0, 0, L. And so the level structure that psi prime maps to is the level structure phi, but post or precomposed by L, right? The action of just multiplication by L. So the target of the dual of psi is actually E, but with a potentially different level structure. So this is something that only comes up in certain examples, because if multiplication by L is in H, then this target is actually the same level structure as where you started. So you've just gone back to where you started and you're just in the usual case. But sometimes multiplication by L is not an element of H. And so you've actually ended up at a different vertex of the graph with level structure. So the point of this operator L that acts on the vertices is to keep track of how the target of the dual depends on the source, right? Because we can see in this case that any edge out of E or E comma phi the dual of that edge will always land at E comma L phi. So the target of where the dual lands only depends on the source of the edge, and not on like any other information. So here's another little picture, right? Just showing those two requirements we had at the end of our definition, just kind of in a little diagram. So if you have an edge E going from the source of E to the target of E, then we require the dual to be a map out of the target. So that's the source of J of E is equal to the target of E. And the target has to be L of the source of E, right? So the squiggly arrow up here indicates that L is not an edge in the graph. It's showing you that this operator L takes the source, to this other vertex 2 away. Okay, so we hope that with these definitions, these abstract isogeny graphs really capture the combinatorial properties we need to talk about non-backtracking walks and spectra of isogeny graphs in more kind of generality to capture level structures, the cases where we have extra automorphisms all at once. And so the first kind of test case, and this is a vaguely worded version of our theorem, but you can check the paper for the details, but is just making sure that isogeny graphs with level structure are actually instances of this abstract isogeny graph definition that we've given. There's a small technical point. I say that if you choose appropriate representatives for the edges in order to define the function j to be the dual map, then the isogeny graphs with level structure are abstract isogeny graphs. This is a technical remark that has already been noted many other places as well, but that the dual map on edges, if you identify isogenies up to post-composition by automorphisms, is already actually not quite well defined in terms of your representatives. So just if you're being very careful, you have to choose a set of representatives. We give a kind of not canonical, but a nice choice of representatives, and it matches up with what was done in the orientations and cycles paper. If referenced that earlier, but if you've read that paper, they give this notion of a safe arbitrary assignment, and that's to deal with exactly this issue. We give a slightly different construction, but it amounts to the same thing. So the point of this theorem is just to say that, okay, our combinatorial structure here of an abstract isogeny graph, it does capture the cases that we're interested in. So that's good, right? And that means that maybe we can study expansion properties, and in particular these zeta functions of graphs with level structure kind of all in one go by studying what happens for these abstract combinatorial objects. So to do that, we need to give a definition of the Ihara zeta function for an abstract isogeny graph. And our definition will look exactly like the original definition, just that now, because we're working with the graph as an abstract isogeny graph, we'll capture what we think of in the isogeny community as kind of the correct notion of backtracking. So we give exactly the same definition, but now just primes are considered non-backtracking with respect to this function j, which can be a little more exotic than it was for the original definition for just undirected graphs. If you take the same product over primes, as a consequence, we have the exact same conditions that, for example, if you take the log and take the derivative, you actually count non-backtracking cycles with respect to this J function. So we can use this to study the distribution of cycles in these abstract isogeny graphs. And another quick teaser that will come back later is that the definition of primes in abstract isogeny graphs matches up exactly with isogeny cycles. So if you've seen this isogeny cycle language before, it showed up in, for example, a recent paper on capital L isogeny graphs where you allow a set of different degrees for your isogenies. The primes in our abstract isogeny graphs are exactly the isogeny cycles, so we can use that connection to kind of bring in results from other papers. So that'll come back as we get towards the applications. So our goal then is to kind of give descriptions of the zeta functions of an abstract isogeny graph in two different ways, and then use these ways to study, say, the asymptotic number of cycles in an isogeny graph. So the two different descriptions are going to be one using combinatorial data. So this will look like that kind of ratio of polynomials that we saw before. Just a little bit more will be going on to capture the kind of increased generality of these abstract isogeny graphs. And then the other is by relating the zeta functions of abstract isogeny graphs to zeta functions of modular curves. And the reason the second one is useful is because by giving a relation between these two things, these zeta functions of modular curves, they're Hasse-Weil zeta functions, like I mentioned way back at the beginning of the talk. And so the coefficients there are capturing point counts on the modular curve over finite fields. And that's something where there's lots of study of like the asymptotics and things like that. So by relating the two, we can take those results on point counts on modular curves and turn them into results about cycle counts in isogeny graphs. So let's start with the combinatorial formula. To do this, we introduce just a little bit of notation. So if you just have a function that's acting on a finite set S, then there's some largest subset where the function acts as a permutation. This is kind of maybe intuitive. You can kind of think of the function as just moving elements of S around, and you can just throw out all of the elements of S that don't have a preimage under F, and you'll get this largest set. And so we give this definition or this notation CKF to be the number of K cycles in this permutation induced by F, right? And then our kind of combinatorial formula for the zeta function of an abstract isogeny graph looks, I will argue, similar to the original, just much more complicated. So in the numerator, we have a bunch of products of hopefully kind of simple polynomials raised to powers, but now our powers involve the number of cycles in the permutations induced by L acting on the vertices and J acting on the edges. So complicated numerator, but that part actually is kind of less important maybe than the denominator, because the denominator is where we kind of capture the spectral properties of the graph. So in the denominator, we have exactly the same formula as before, except that the u squared term is now multiplied by this capital L. And so just to make sure it's understandable what this means, remember that the adjacency matrix is an operator on the vector space whose basis is the vertices of the graph, right? So you can think of it as a number of vertices by number of vertices square matrix. And the same thing is true for L. It acts on the vertices, so you can write it as a matrix of the same exact size, And then this determinant is just a determinant of square matrices of size the number of vertices. So this looks nasty. It turns out that it does simplify significantly in a lot of cases. So for example, if you assume that your graph is not just like an abstract isogeny graph, but actually satisfies all the properties to be a graph in the sense of Serre, then this ends up being exactly the formula we saw at the beginning of the talk for the original Ihara zeta function. So it really is a generalization. But even in some of the cases of graphs with level structure, we can give kind of a nicer formula for this. And to do that, we introduce things we call the orientable graphs associated to an abstract isogeny graph. So the term orientable comes from the graph literature and connections to topology. So we can kind of ignore that for now. What we want to do with these orientable graphs is make like an undirected graph out of the isogeny graph. And the basic idea, the definition is quite long, but the basic idea is that once you kind of collapse all of the action of L on vertices into one vertex, so you identify in, say, the graph of level structure, you identify E phi with EL phi, right? And then you also identify edges with what happens to them under double duals. Then all you're left with to deal with is these loops that are equal to their own duals. And there's kind of two natural choices for what you can do with those. Either you can just throw them out, or you can add an artificial kind of copy of them and say that your dual map just switches those two. So gamma plus 1 throws them out, gamma minus 1 adds the artificial copy. And yeah. And so in a lot of cases, the formula that I showed before that looked pretty nasty simplifies by using these orientable graphs. So say that your isogeny graph is d-regular and that this induced permutation is an involution and the source of j squared is equal to the source of y, then the Ihara zeta function can be written as just 1 plus u to the Euler characteristic of one of these orientable graphs times 1 minus u to the Euler characteristic of the other. And then the denominator, you have the determinant of exactly what shows up in the original Ihara determinant formula. So I realize this q I didn't define here, but q is just the scalar matrix that multiplies by d minus 1. So it's the same thing that showed up earlier. Okay, so if our graphs are nice enough, then we don't have to deal with that whole messy formula from the previous theorem. But I wanted it to be on there so that people think it's really impressive because it's lots of generality and hard looking formulas, right? But most of the cases we care about, we don't actually need to think about. Great. So so now we want to move on to kind of the second goal, which is relating these Ihara zeta functions to Hasave zeta functions of modular curves. And like I mentioned earlier, the point of doing this is to understand asymptotics of cycles in graphs with level structure by relating them to point counts on modular curves. So to do that, we'll give a formula where we write down the product of the Ihara zeta function of an abstract isogeny graph with some Hasave zeta functions. So we, for technical reasons, we need our H to be between the Borel level structure and what I believe is called arithmetic level structure. So on the right, the level structure is identifying a cyclic subgroup of size n in the n torsion. And on the left, it's identifying a point of order n. So as long as your H is kind of not worse than the level structure that identifies a particular point, then we can get this theorem. And we let HP be the product of H with the subgroup that represents Borel level structure. And I'll note that this product really lives in GL2 Z mod PNZ instead of z mod nz, just in case you're worried about where that product is. And so what's the theorem? Well, you take the modular curves that are associated to these two subgroups. So here I'm, for the interests of time and everything, I'm going to assume some familiarity with modular curves. If you don't know modular curves, just believe me that there are really nice equations that you can write down that are related to these curves with level structure and parameterize elliptic curves with level structure. And the formula that relates the zeta function to these the zeta functions of these modular curves is given by this product here, where the zeta function times a ratio of these two Hasse-Weil zeta functions is equal to, again, a complicated looking formula, but a rational function that just depends on the kind of combinatorial data in your graph. So this J and L function and the cycles within them. And again, we don't really have to look at this whole messy formula at the bottom here in every case. In a lot of cases, we can give a simpler formula when we move to these orientable graphs. So a corollary of that, we look at the graphs with Borel level structure. And here x naught of Pn is just the modular curve associated to B naught of Pn and x naught of n to B naught of n. And in this case, right, that product formula ends up simplifying to the product of the zeta function with this ratio of Hasse-Weil zeta functions is this nice thing where you can just see 1 plus u and 1 minus u showing up. And I'll just briefly point out, because I forgot to mention it earlier, that the reason that we use g to the -1 and g to the +1 in this notation is so that they line up with telling you things about the orders of the poles at u equals -1 and u equals 1. Just in case that notation was like not clear. Okay, so we've covered a lot of things, but we have this combinatorial formula, which tells us that, you know, we can kind of get ideally explicit counts for the constants that show up there. And then we have this product formula that relates our zeta function for our graph to zeta functions of modular curves. And what we want to do with these is study asymptotics of the things involved, right? Because that's what you do with zeta functions. So what we're going to do is we're going to use these to deduce results about the number of cycles of length r as r goes to infinity. And there were already some known results about this in the literature, but they were limited to the case P is 1 mod 12 and also to just the base isogeny graph GPL, right? So we're able to remove those restrictions on P and also generalize to more level structures. So what we do to get this is we use that formula that I put on the previous slide, and we use that to deduce a relationship between the number of cycles and the number of point counts, or the number of points on modular curves. So we get the number of non-backtracking tailless cycles of length r in the isogeny graph with Borel level structure can be written as this formula where the first two terms just depend on the number of points on a modular curve, and then the last two terms are just using these Euler characteristics, so some invariants that are associated to the graph, right? And we actually show in this case with Borel level structure that these Euler characteristics, you can give pretty nice clean formulas for them. Well, clean is maybe an exaggeration, explicit formulas for them that are not too hard to compute in practice. And so the previous theorem gives us this asymptotic. So the number, we look at the number of cycles, non-backtracking and tailless of length r, and asymptotically, that approaches L to the r as r goes to infinity. And you get this just by using things like Haas's theorem that count the number of points on a curve and looking at the asymptotics of the right-hand side of that formula versus the left. So my last one slide-ish is just another application I think is quite interesting. It gets us kind of away from the isogeny graphs, but we kind of flip the script and say, maybe we can use isogeny graphs to study modular curves, right? And so this is a formula where we take n equals 1 in the previous thing, and we use that to look at the number of points on the modular curve with Borel p level structure over the finite field of size L to the R. And we give that in terms of cycles in the isogeny graph. And then those cycles, by work of other people, the Orientations and Cycles paper, or Wissam Gantos has some papers on counting cycles using Brandt matrices. Those tell you that the cycles in isogeny graphs can be counted using class numbers of imaginary quadratic orders. And so you can actually get a formula for the number of points on a modular curve over a finite field in terms of these Euler characteristics, and then a set of class numbers that you can describe. And number theoretically, like why this would be true, I have no idea. And I asked Drew Sutherland, and he also had no idea. So probably that means that nobody does. So I think it's a, an intriguing thing if you are interested in modular curves. All right. Hope that was motivating to be into zeta functions, and thank you for listening, and thanks again for inviting.
Great, thank you. As always, if you have a question, feel free to unmute yourself or ask a question in the chat. Maybe while people are writing or thinking, I can ask the first question. I guess a more general question, like this definition of an abstract isogeny graph seems to like capture a lot of different things in one go, which is kind of cool. And it seems you were able to do something very concrete with it, like still work with it. So it's still like, yeah, not too abstract to work with. Did you think of any other places where you could work with this definition? Like any other applications?
That's a good question, both in terms of like, so I mean, one application in kind of isogeny-based cryptography that I think is not far from what's already in our paper, but we just kind of didn't want to add yet another thing because it's already a bit of a long paper, is getting these results about isogeny graphs with level structure being Ramanujan that appeared in the Codoni-Lido paper. So they proved for like a large class of level structures that the graphs are Ramanujan.
Yeah.
And you should be able to deduce that from this relationship between the zeta function and the zeta functions of modular curves, and then using Deline's bounds on basically the Riemann hypothesis for the modular curves. So I think you should get kind of a one-go proof of Ramanujanness that applies for at least the ones in Codoni-Lido and maybe some other ones, although there's probably some subtleties there. And then the other thing that's related to that, I think, is expansion properties, not just of random walks, but of random, like non-backtracking random walks. So this is again like what happened in the supersingular elliptic curves. You can trust paper. They needed to think about specifically non-backtracking walks, which we know generally that these walks expand better than just random walks in graphs. But in these situations like the higher dimensional graphs and the graphs with level structure, the non-backtracking walks that you want to consider are like a little bit different. And so yeah, I think there's a potentially neat framework using these to study like the expansion properties of those graphs, or excuse me, those walks within isogeny graphs. In terms of other things that like fall under this definition, like other kinds of graphs we might care about, I don't know. It would be cool if somebody finds some other kind of graph somewhere else in math or in cryptography that is also one of these in some natural way, but I have no idea.
Yeah. I mean, you already capture a lot of different graphs, so I think it's already like pretty useful as a framework, even without adding another one into that. But yeah, sounds cool. Any other questions?
Maybe I could ask a question. So, in like just the last formula you showed for the number of points and relating it to different class numbers, did you try like plugging in some very like simple modular curves where we know the number of points very well and like see if it tells you something funny about how class numbers relate or
I mean, we have an example in the paper where we just take a modular curve where you have like a known equation and you actually look at like the points over a finite field and count them, and then you count on the other side.
Mm.
That's more of just kind of like uh, a check to make sure that we got all the constants right.
Yeah.
Yeah, I don't know about, using this for studying class numbers. I think it's probably more likely to go in the other direction because you have like the sums of class numbers on one side, so they all get kind of mixed up. But yeah, I don't know. This is like kind of something that popped out and was, is kind of at the end of the paper, and uh I think there's probably a lot to
Mm.
do with this because it's the kind of thing that seems like, why would this exist? And then it just comes from doing this combinatoric stuff. Um, but I don't know exactly what the best direction to go for applications of it is.
Oh, interesting, interesting. I just ask because like there's for instance sometimes like there's for instance this like Eichler mass formula which basically like is an example of the fact that the actually saying something about class numbers are they're kind of random and very hard to say something about, but certain sums of class numbers are very well behaved and this feels like kind of like in my naive thinking and like squinting at it feels like kind of a generalization or a similar phenomenon.
Yeah. Yeah, I mean it definitely, and it is related in that like the way you get the sum of class numbers is by, at least the way I think of it, as you're thinking of cycles of length r as being related to class group actions in like the oriented graph,
Mhm.
right? So it's like the same flavor of, you're looking at orientations and optimal embeddings that gives you like these Eichler mass formula type results.
Mhm. Oh, okay, very cool.
Can I ask a question?
Yeah.
Yeah.
So could you go back to the formula relating the Hasse-Weil zeta function and yeah, so
This
this
one,
one
or
and then the other one.
yeah,
So
this is the
here
other
you
one.
have an infinite product, but everything is supposed to be rational. So I think that means that the size of the orbits of L and J are upper bounded.
Yes. Yeah. I mean
Uh,
the
so
um your graphs will all be finite. So like L and J are acting on finite sets. And so there will only be a finite number of lengths that actually appear.
okay, yeah, that's pretty trivial. Yeah. I was thinking if they're bounded even uniformly across P, and that may actually be true because so as far as I understand, you're just bouncing between two J invariants, but you're changing the level structure every time, possibly, right?
Yeah.
So
Yes.
then,
So yeah, I was gonna say there's like a couple of examples where we work out this product a little bit more explicitly in the paper by doing these kinds of things where we say like, okay, if we put the right like residue conditions on L and P, and we look at this particular level structure, we can actually say what the cycle types look like. Like they'll have to do with, say, the order of multiplication by L in the level structure subgroup, or things like that. Yeah, and so I think you're right about like being bounded uniformly on P if you fix a level structure. We definitely do this in some cases. I would guess for any choice of fixed level structure, you could say that there will be like a uniform upper bound on how big the length of the cycles in the dual and in the L function will be.
Mm-hmm. Yeah, and then is there, so in the next one, the product disappeared. Is there, I don't immediately see the relationship between the two formulas. Is there an easy way to?
Yeah. So basically the Borel level structure is a nice enough case that basically you'll only have K being like 1 or 2 in the product. And so the Euler characteristics show up. It might actually be easier to see kind of why these Euler characteristics show up if I go back to the combinatorial formula. So in this, if you look at the numerator, right, the original Ihara determinant formula, you got the Euler characteristic of the graph showing up. If you think of this as being like an undirected graph, so J is just a fixed point free involution, then L is the identity. So all of the cycles in L are length 1, and there's the number of vertices, many of them. So you get a 1 minus u squared to the number of vertices, and then all of the L terms in the product vanish. And then all of the cycles in J, if you're a fixed point free involution, have length 2. So the 1 plus u for length 1 cycles contributes nothing. And then the function over here gives you a 1 minus u squared to the number of cycles of length 2, which is half the number of edges. And when you put those two together, you end up with an Euler characteristic, right? Number of vertices minus half the number of edges. So it's a similar kind of thing to get from here to here, but now you have to throw in the Euler characteristics of these undirected graphs are like similar to the Euler characteristic of the original graph, but then with some factors involving the number of fixed points that they're allowed to have. And that's kind of, you put enough nice assumptions, then you do this like simplification and the Euler characteristics show up.
Yeah. Cool, thank you.
Yeah.
Any other questions? Okay, if not, thank you again, Eli, for your talk. So in 2 weeks, we'll have our next talk, which will be given by Ilinka Radulescu about forensic categories, which is a framework for ski-sign-like primitives. So hope to see you all back here in 2 weeks. Let me recording.